So here are your two starter problems. Voices off, thanks. Here are your two starter problems. It was calculate the degree measurement, one would assume you understood, of pi on 4 and then 3 pi on 4. I chose pi on 4 because it's one of the really common angle measurements that you'll actually, by the end of this course, you'll know off by heart what it is without even doing any calculations. You'll just go, pi on 4, 45 degrees, too easy. So the way we calculate it is we take the angle that we're given, I'll keep it in red, pi on 4, and we now need to multiply it by 180 over pi. I guess the way to look at it, even though last lesson I know I showed you an example of a radian measure without pi's in it, but kind of think of it like, which way is it? Is it pi on 180 or 180 on pi? Almost always you're cancelling out a pi. So it makes sense for the pi to be on the bottom to change it into degrees. I hope that makes sense because you're going to be removing that pi. So cancel out the pi's, and you're working out how many times 4 goes into 180. 4 goes into 180, carry the 3, 45 times. Although generally you could just do it in 2 steps if you don't know that 4 times 45 is 180. I don't know if I would. 4 goes, they're both even numbers, so halve it, and I'd get 2 and 90, and then halve them again, and I'd get 1 and 45. So whichever way you look at it, you end up with a final answer. I'll go sideways just for the room's sake. Normally we do equal signs underneath each other. We get pi on 4 equal 45 degrees. Any questions? Now, just because this will make it really good. Oh, no, I'll finish this off first. 3 pi on 4. You could use the same method. Don't write this down if you haven't got there yet. But if you started off with 3 pi on 4 times 180 on pi, that's not bad. Cancel out the pi's. 4 goes into 180 45 times, and 3 times 45 is equal to 135 degrees. Okay, you could do it that way. But if your maths is strong enough, your fraction knowledge is strong enough, and PS, those who have weak fraction knowledge still, this makes this unit much harder, I think, because radian measure often deals with a fraction. And so if you're kind of a little bit like, what I'm about to show you, if you're going, you did what now, how now? Then I would suggest that you probably need to do some remedial work on fractions. Good news is everyone can do it. Everyone can get better at it. Bad news is it's not going to happen by osmosis. You actually have to work at it. So with a 3 pi on 4, I could just take out the 3 like so. I could say it's 3 lots of pi on 4, which must be pi on 4 is 45 degrees. So I'll write it down, but I will just do that bit in my head, which is 75 degrees. So rather than having to apply, 135 degrees. So rather than having to apply the formula in a rather clunky way, I can use a result that I've previously got in order to just quickly add up, or in this case, multiply to get the resultant degrees, 135. Mitch? How is that easy? Isn't it like the same? No, I disagree. I think because you've already got the result of pi on 4 equals 45 degrees, saying what's 3 lots of 45 degrees is a lot faster than applying a formula, cancelling down yet again, doing the same thing as you did here, but doing it yet again. It seems to me like more work. Yeah, no, absolutely legit question. It's a really common one. Often when I say these things, students will say that they won't even say it. So I'm glad you did. But they'll think, well, it seems to be easier if I just apply a formula over and over and over again. But what that is that's a workhorse mentality. Just think smarter and it's more efficient. Particularly since pi on 4 is going to be one of those really common ones. Pi on 3, pi on 6, pi on 4 are really common. And you'll see that with these solutions here. These are the solutions from last lesson. Please feel free to write them down if you didn't get them or to tick them off. They were supposed to be completed for homework. So please feel free to write next to your work, wasn't sure or I am a slacker if you didn't complete them. They're the only 2 excuses you've got. Not I was too busy, because really it was about 10 minutes work tops. And if you're too busy for doing 10 minutes maths of work, you're just too busy for life, guys. What can I say? It's too busy for life. Each of those problems there, questions 1, 2, and 3, are very common. So 1, 2, 3, and 4 are really common. They're so common that by the end of this course, Mitch, by the end of this course, I'm confident that you will know the radians and degree measures of those things without too much effort at all. You'll have them to memory because we come across them a lot. So knowing that pi on 3 is 60 degrees, pi on 6 is 30 degrees, pi on 4 is 40 degrees, pi on 2 is 90, and therefore pi is 180, 3 pi on 2 is 270, and 2 pi is 360. You will, I sincerely hope you will have them committed to memory by the end of this course, just through use, not through anything else. But it kind of makes like question 5 here an example of what Mitch was asking me before. So if I was given 2 pi on 3, if I was given 2 pi on 3 and I needed to work out what the angle measurement is, then I should know that pi on 3 is 60 degrees. So if I've got 2 pi on 3, that's going to be 2 lots of pi on 3. So it's just going to be 120 degrees. That's the kind of thing I'm talking about in terms of efficiency. Agreed that efficiency really only comes to the fore when you already know that pi on 3 is 60, pi on 4 is 45, and so on. Similarly for question 7, and I won't bother with question 6 because it's kind of a similar idea, but with question 7, 75 degrees, I'm doing this on the board, just saying this for the video, 75 degrees is actually just 2 of those common angles combined. What are the 2 angles combined there? 45 and 30, right? So I've got 45 and 30. Now, again, just imagine you fast forwarded a little bit and these values are so common that you now know them without thinking too hard about them. Then I can say 75 degrees is pi on 4, 30 degrees is pi on 6, and then I can go, well, that's 4 3s, that's 3 pi plus 2 pi on 12. That could be an in your head operation. So it's 5 pi on 12. Now, you still may be thinking, but that seems to be harder than just applying the formula. Can I put it to you guys that if you feel that adding these 2 together to get 5 pi on 12 is harder than applying the formula and cancelling down the fractions and stuff, can I suggest that demonstrates a weakness in fractions for you? So the stronger your fraction knowledge is, the more efficient you can work, because this is just like nothing. This doesn't raise a sweat. But if this makes you feel like you might have a nightmare tonight seeing me do that, can I suggest that you focus on your fraction, doing some remediation around your fractions? The other thing I want, I'll shut up for a moment and I'll just ask if there are any questions. Okay, the other thing I wanted to point out, this is a really common, it's not an error. It's just a way you were thinking that needs to be changed. When you went from from degrees to radians, I'm doing 120 degrees on the board and I want to convert it. So we do 120, it should be 60 pi on 3 plus pi on 3 really, so it will be 2 pi on 3. But I'm going to do it the old way just to show you what I mean. So 120 times pi on 180. What I noticed a whole bunch of people doing was reaching for the calculator and literally doing and getting a decimal out of it. But almost always you want an exact answer. And because pi is cannot be written exactly, you know, it's 3.1415 and it goes on forever, then an exact answer would require you to leave it with a pi in the final line. Okay, so you can't reach for your calculator. It's absolutely legitimate to ask you to do this in the non-calculator section. And even if it's in the calculator section, although you might be able to work out the fraction easily on your calculator, anyone who puts a decimal down will definitely lose a mark or half a mark or something. What do we do then? We have to use cancelling down ideas. We need to look for a number that goes into 120 that also goes into 180, like 60. 60 goes into 120 twice, goes into 183 times, multiply the tops here to get 2 pi, and multiply the bottom, nothing. Well, not nothing, it's on 1. 1 times 3 is 3. So it's 2 pi on 3. Okay, again, if that looked really hairy and scary, it's again probably more likely to be your underlying fraction confidence as opposed to what I'm doing here is really complex. Any questions before we move on to today's learning? Did I screw up somewhere? 3 pi on 2. So that's a 2, that's a 7, that's a 1, that's a 2. Okay, anything else? It's all right, it's not like we've recorded it for everyone to hear later, Charlie. So it's fine. So, oh, did I mention his name, did I? Sorry, Charlie, I didn't mean to mention your name in the video as well. That was going to be anonymous until I mentioned Charlie's name. So let's move on to today's learning. And I just want to make sure that we're really solid on this. And if you feel the need to write this into your summary book, now's the time to go. Sorry, Charlie. Now's the time to get your summary book out. Today we're going to have a look at the sine rule. And then in tomorrow's lesson, we're going to have a look at the cosine rule. Now, I think all grade 10 math students have seen this before. I don't think it's a core-only principle. If you've done Maths Extended, you have definitely seen these rules. They're not that bad, guys. These are definitely almost always calculator operations. And what they allow us to do, the sine and cosine rule, is they allow us to calculate missing lengths or missing sides when the triangle is not a right angle triangle. So it's really powerful from that perspective. We no longer have to find right angles as long as we can determine certain properties of the triangle we've got in front of us. What I'll probably do is I'll probably update the learning schedule with an optional video for you to watch, which explains how the sine rule and the cosine rule is constructed from scratch. I find that for some students for any student who wants to take the time to watch and understand, constructing these or learning how to construct these rules for yourself tends to do at least as much, if not more benefit than doing extra problems. Because if you construct it for yourself, you see how it's created, you get a sense of the rule, and therefore your ability to apply the rule tends to be much more efficient, I find, or much more deeper connection. Whereas if you're just applying a rule, it tends to be a little bit script monkey. So labeling a triangle, I find that students really struggle sometimes with putting these things together. So the first thing we're going to do is we're going to label the vertices, which are where the two sides of the triangle meet. The corner of a triangle is a vertex. I'll do it in black because it stands out best, but I hope that's okay. So it doesn't matter what corner you start on. I'm going to start on the left-hand corner, or left-hand vertex, and we always label our vertices with a capital letter. So this will be capital A here for this vertex. Again, which of those corners you label A in front of you, I don't mind. If you like the A being on top, that's fine. If you're a right to left thinker and you want to put the A on the right, that's fine as well. Typically, once we've labelled the first one, we go around in clockwise, but again, it doesn't really matter. So I would label the top one here B and the bottom one here C. And we would describe this as triangle A, B, C, like so. So if you're communicating to someone else, like you're writing it down, and you need to say in triangle B, in this triangle, you could use triangle ABC like I've written there. Now here's the critical thing. The sides are always labelled, well, not always, are usually labelled with the lowercase letter that is opposite the vertex. Okay? So that means that between B and C, we would label it with a lowercase a. Between A and C, it will be a lowercase b. And between A and B, it's a lowercase c, like so. Now, it's really important that you stick to these standards. It's really important, like I have seen some people throughout the year interchangeably use capital letters and lowercase letters. It's horrifying when you do it to start a sentence in your report, by the way. But that aside, I have seen people use capital A for area and then little a for area. That's not as common as big V for volume and then a little v halfway through the problem. For this, you've got to break yourself of the habit. because capital A stands for the vertex in a triangle, little a stands for the length of the side that's opposite that vertex. We also use big A, big C, big B, and big C to represent the angle. It's a bit loose, describing the angle as sine of A, sine of big A, but nevertheless, we do that to save a bit of time. The full thing would be to call it angle BAC. So angle B, I don't know if that, I probably haven't done that enough. Angle BAC would be the full way of describing that angle there. But when we're doing a bit of a shortcut, which is what we're about to do with the sine rule, we tend to just call it A, the angle at vertex A. Any questions? So here's the rule. I'll zoom out so you can see the whole lot at once. The sine rule has two forms. They are written like this in your information sheet, but I need to do a bit of explanation afterwards. We have the side length A divided by the sine of the angle opposite, so big A. That ratio, A over sine A, is the same value, that's what equals means, as B over sine B is the same value as C over sine C. Why? You have to watch the video to find out. But that's the rule. Now you can see at the top corner there, I've got pick a pair. Because I notice in past years, students get a bit confused because there's two equal signs on the one line, which is weird, because normally we go equal signs underneath each other. But they also try to fill in all the blanks here. So pick a pair is a really important point here. The idea is that one of these pairs can be set equal to another of these pairs, and if only one of the four things is unknown, we can solve for the unknown. So if I know what the side length of A is, and I know what the angle opposite it is, and I know what the angle opposite C is, then I can work out C. So this, what I'm circling here, is the same as this here. Okay? So this equals this equals that. This equals this equals that. They are all equal to each other. That's what that rule is designed to show. Questions? You can see I've said two forms there, and it's a very trivial thing to flip every single one of those fractions and say they must be still equal to each other. So a third is equal to 2/6, and 3/1 is equal to 6/2, that kind of thing. If we flip every single fraction, they're going to be equal as well. So we have sine of A, big A, capital A, over little a equals sine of big B over little b equals sine of big C over little c. Both of these forms are on your information sheet. So you have to memorize them, but you have to understand how they work. Here's a question for you. Why on earth is it useful to have two forms? When might I use the top form and when might I use the bottom form? If you've done maths already, this kind of maths already, you probably know the answer. Reese.
On the side length of the angle.
Spot on. Top one for side unknown side length, bottom one for unknown angle. Can you use the top one to find an unknown angle?
Yeah.
Starts with Y, rhymes with best.
Yeah.
Yes, you can. Yeah, it just means that the unknown is going to be on the denominator of the fraction, so there's an extra line to get it to work. That's all. That doesn't matter. Any questions? Sorry?
No.
Okay. So let's have a look at a couple of examples, and then I'm going to get you to work off the worksheet that I've handed out to you already. So here's the example. I'll just zoom up for a little bit, then I'll zoom out again because there's nothing to see at the moment. So we have got a triangle, and we have 7.6 as one of the lengths. We have 118 degrees as this angle in here. We have 25 degrees as this angle here. And we have an unknown side length x here. So before you get too caught up in the formula, I wanted to sort of explain what you're looking for. You're looking for pairs. You're looking for an angle and its opposite side. Okay? That's what you're matching up. Yes, you will have the formulas, but sometimes they can trick you by putting a C opposite angle A. That shouldn't throw you, because although those letters are designed to show you the relationship between everything, this is the key thing you need to look for. The side length and its opposite angle. What have I got? I've got the side length 7.6. So what is the opposite angle? 25, good. I've got the unknown side length x. What is its opposite angle? 118. So there, they are my pairs. What I could have done is I could have, oh, hang on, someone do it for me. 118 plus 25 is 143? What's 143 minus 180 minus 143? 17? No. 37? So what I could have done, is I could have given you that. I could have given you the two angles there, 25 degrees and 37 degrees. So 25 is matched up with 7.6. X is matched up with nothing yet. Okay? So my point is, I don't match up X with 37 degrees because 37 is not opposite X. But I do have the two base angles, well, not base, but I do have these two angles here, which means therefore I can work out this top angle even if I'm not given it. So I could, for example, put a theta in and say theta is equal to 118 degrees. Does that kind of make sense? So don't just look at the numbers I have and the numbers I don't have. You're always going match the side with the opposite angle, match the side with the opposite angle. So here we go. Oh, I was going to make a comment about that, so I will. Oops, math. There's a little bit of muttering going on. I feel so rude because I seem to be talking over people's important conversations. So I'll just wait for people to be quiet. I apologise in advance for talking over you. Thank you. Can I continue now? Awesome. Okay, so slide 3. We have this. So we're going to do the matchup. So it doesn't matter which order you do it, it's in left or right, but I'm going to start with the unknown on the left because that tends to appeal to me. So we've got x over sine of 118 degrees is equal to, it's important to put those measurements in, so I put in those units of measurement in because we need to make sure we're not dealing in radians, sine of 25 degrees. Now, for some students, and this is reasonably fine, what some students like to do is they like to calculate, like you get out their calculator and calculate all these numbers up first. So they'll go 7.6 over sine 25 and they'll come up with a number here. And they'll go sine 118 and they'll come up with a decimal number here. That's okay if you want to do that. Do note that unless you're keeping the values in your calculator's memory, if you do all this kind of stuff and then just keep on typing out the rounded numbers, you're bound to have rounding errors and you'll lose half a mark or something as a result. So if you can stomach it, it's better if you do the manipulation first to make x the subject of the equation. In this case, I'm going to multiply both sides by sine of 118. So I get this. Like so. And then I can plug that into my calculator. Bip, 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 bip. Away we go. You'd go 7.6 multiplied by sine 118. Oh, check top right corner. Yes, it's in degrees. I'm all good. Divided by sine of 25. Enter. then you'd get a number, and that number would be, drum roll please. That was a really, thank you. There was one person doing a drum roll, and this is why I do videos, because then I can at least entertain myself. Okay, 15.88 meters would be what you get out of your calculator. All good with that? Cool. I'm going to do the next one really quickly because I've now done my 15 minutes of instruction. In this example, you've got your unknown angle here. So you've got theta, and the opposite side is? Great. And what's the other pair? Are you sure those two things are opposite each other? Yes, you are. They are. Yeah, good. So what am I going to use, form 1 or form 2? Well, I used form 1 before. It's form 2 because the angle is the unknown thing. So we would say sine of theta. Form 1 if you've got an unknown side. Form 2 if you've got an unknown angle. You can use either form and it will work still, as long you just got a bit more work to do. Equals sine of 120 over 5.8. Mitch. Okay, M. Sorry, it's a bit off the screen, but is that okay? Everyone got that? Okay, I'll rush through it. Sine of theta is equal to, so again, I encourage, if you can handle it, to do the manipulation as late as you can. Now, this is where I'd probably go straight to theta. I'd use my calculator, and then I would go bip, 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 and out would come, to the nearest degree, I think it is nearest degree for this one, 21 degrees. Now, the bip, bip, bip is this thing here. On my calculator, I'm going to use the sine inverse button, which I showed you yesterday, and then inside the brackets, I'm going to put that whole big old thing. 2.4 sine 120 degrees all over 2.4, or divided by 2.4, close the bracket on my sine inverse, press return, and as long as it's in degrees, you will get 21 degrees out of it. These are two basic examples of how to use the sine rule to solve problems. Mitch? Yes, yep, thank you. Good pickup. Okay, that aside, they are two basic examples of how to use the sine rule. What I handed out to you in class was this worksheet here. Another good video moment. But the worksheet, guys, just focus. The worksheet starts with the cosine rule. Please don't start doing this, even if you know the cosine rule, because I want to see you practicing the sine rule. So you need to go to the sine rule, which is on the next page, please. In terms of what you need to do, can I suggest, as a bare minimum, how about we just say, for question 7, just do that right-hand column, D, H, and L. So just those 3 basic ones, and then do 7, 8, and 9. Yeah. And I'll come around and help you.
Is this from the general maths